Please work. It's working, yes. So I think I mentioned this yesterday, but yeah, if you get pulled out of class, or you're sick at home, whatever, if you miss class, you can, or you're at sports, whatever, you can hopefully go on Google Classroom. There's a link to like a, they will be live, I think. But anyway, you'll see a play. You can open up a playlist and watch them later if you want. So if you miss class, you can go and watch them and see what you missed, if you want. Okay, so yesterday I very briefly went over this question, and I was like, just think about this. Just think about why this function might look something like this. So this is x value of 3. Let's actually draw 3 dash marks and then 1 dash mark. So -1, 3, y-intercept was 9, and it looked something like that, right? Remember that from yesterday? So if I wanted to be, so when you graph these, it's not like an exercise in super precision. We just care about we're caring about the general properties of it. So things like end behavior, regions where the function is positive versus regions where the function is negative, things like that. So if you say graph this on a computer to check your answer, and you go, oh, actually it was slightly different looking, it's not usually a big deal. We're just caring about like the nature of these zeros is a big concern for us. The end behavior and like y-intercept, just stuff like that. So just keep that in mind. You don't, if you check your answer, you don't need to go back and like make sure it's perfect. So especially because a lot of these you're going to end up with pretty big y values, and so we don't really care so much about like how high does this hump go. Does that make sense? What I'm talking about? Okay, so there is one little thing. It's not super critical, but I think it's really fascinating. So I wanted to share it with you. If you graph this. I didn't give you I left one little thing out, which is actually at this location, it still just passes through the x-axis, but it actually passes through kind of like this. You're like, okay, there's a little wiggle in there. Like, okay, sweet. But I wanted to point it out because I think it's really interesting. So look at these two pieces that created this function. Lost my red card. Do you guys all understand? I hope you do at this point. If I were to graph this function by itself, what does it look like? Yes. And the thing I really want to focus on is I don't really care about the rest of the parabola. I care about this little neighborhood here. I care about what's happening at the x-intercept. So what happened at the x-intercept? It bounced off. You see what I'm talking about? So if you want to be all technical, you can say, oh, it had a 0 with a multiplicity of 2. We don't need to be all technical like that. We can say it bounced, or I do like to say something like a double root. Okay. Now, so what causes that? Well, let me know if this explanation makes any sense. So on the right and the left of this, so again, where does the x-intercept happen? 3. So think about a number just to the right of 3, just barely, like 3.1. If you plug in 3.1 in here, would the result be positive or negative? Positive, right? Because it's getting squared. Yeah. You can be pretty confident that no matter what you plug in there other than 3, if you plug in any number other than 3, because it's getting squared, it's going to be positive on both sides, right? So, okay, so plug in 3.1, you get a positive. Plug in 2.9, number on the left of 3, it's also positive, right? So that's the kind of behavior that generates this sort of bouncing off structure. And ultimately comes down to this number here, right? So think about how you generalize that. If this number is, what word am I looking for? Anyone? Even. Very good. So if that number is even, it results in this double root phenomenon, where it's going to come down, it's going to touch the axis, and then come back the way it came from. Compare that to x plus 1 cubed. Of course, the 3 is odd. So you might go, okay, well, I guess if even does that behavior, odd is going to be some kind of contrasting behavior. So what does this graph look like? It's this guy.
Yeah.
Shifted left 1, right? So it looks something like this. Again, I don't really care so much about the rest of the graph. I'm really interested in this behavior. How does this thing interact with the x-axis? Now, do you see how the same argument you can apply it? So, like, let's say x was negative 0.9. If x is negative 0.9, you get a positive. But if x is, say, negative 1.1, since you're cubing, it would actually be a negative. Does that make sense? So what that tells us is that at negative 1, it's going to change from positive to negative or negative to positive. It's going to actually pass through. So here, it's not going to bounce. It's going to pass through the x-axis. That's a weird letter. Pass through. Anyway, the part that I wanted to share with you that I thought was really interesting is, do you see how you can actually see that sort of wiggly behavior? In calculus, we call it concavity. As concavity for like, is it curving down, is it curving up kind of thing, but I don't need to worry about that. But anyway, I just thought it was neat to point out. So anyway, the term that created the bounce, you can see why that happened. The term that created the pass through, sorry, this term creates the pass through, we can see where that came from. How did we get the y-intercept of 9? How do you find that?
Zero.
Very good. You just plug in 0 for x. That's just easy peasy, right? So what does it mean to be a y-intercept? Well, it means your x value is 0, right? So simply plug a 0 in here in both spots, and you'd have negative 3 squared times 1 cubed, which of course is 9. And the last thing we talked about very briefly yesterday was, if I were to expand this, I won't ask you to, that would be highly sadistic. But what would be the first term in the expansion? X to the 5th. Just for fun, I'll do a brief explanation of what that looks like. So let's say you did have to expand that. It'd be pretty tedious. So to expand this, you'd have to first expand this, x squared minus 6x plus 9. Then you'd have to expand this, which would turn out to be x cubed plus 3x squared plus 3x plus 1. And then what would you have to do? You have to multiply these, and you have to go this times this, 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 this times this. Woo. So 12 multiplications. Then you have to combine like terms. Long story short, dot, dot, dot. You see how the first term really just comes down to like, so this x squared came from x squared. This x cubed came from x cubed. And so in this expansion, x to the 5th would be the largest degree term. Is everyone cool with that idea? That makes sense? Okay. Now, why do we care about that in terms, in order to understand the graph? Well, what does x to the 5th look like? What I really care about is this end behavior. Anything with an x to the 5th as the dominant term has this kind of end behavior. He goes to positive infinity on the right, and he goes to negative infinity on the left. Now, if you have a whole bunch of extra terms in there, could he potentially look like this? Could he look all wiggly like that? Sure he could. But he still has that same end behavior. He's going to infinity on the right, he's going to negative infinity on the left. Does it still make sense to everyone? Okay, so then the final process when you're trying to visualize a graph like this is you're putting together this, the end behavior, the bounciness or the pass-throughiness of the roots with the y-intercept, and it all has to fit together. So let's do another example. And then I want to give you guys some time to try some on your own, and we'll check answers and all that good stuff. Okay, let's try 10. As an example. Before we move on, did any of that raise any questions? Anyone confused about anything? Oakley cadokley. Okay. Who can tell me like just one fact about this function? What it's called?
There's a 0, 1 over 0 is 4.
Very good.
The y-intercept is 2.
So Alyssa got us one of the x-intercepts at 4. What'd you say, Julia?
I said the y-intercept is 15, I mean negative 15, so what I could do. Because I just plugged it in. It's I got positive 16.
It's positive.
Oh,
You
yeah.
got the right idea though. So let's make sure so when we plug it in, it would be, so for for the y-intercept, you have 2 times 0 plus 1. Sorry, that sounds, sorry. 1, so you have 1 squared times negative 4 squared, which of course is 16. So the y-intercept would be, but good, thinking about getting the y-intercept, so that's good to have. Really all I care about is that it's a positive number. I just want to know, is the y-intercept above the x-axis, below the x-axis, or is it maybe on the x-axis is the origin? That's really all I care about. Don't try to make the graphs to scale. It's torturous. By the way, what kind of 0 is this? Is this a bounce 0 or a pass-through 0? Bounce. This 2 tells us that it's going to bounce there. So I can make myself a note, maybe. It's going to bounce. Very good. There's also going to be a 0. It does say label your intercept, so I'll do that. I'll be good. Now is it going to bounce there or not? Yeah, because of the 2. It's also going to bounce here. So we have 2 bounce. We have 2 double roots. Let's get end behavior. So if I were to expand this, what would be the lead term? Yeah. Technically, if it would be 4x to the 4th because of you'd be squaring 2x to get 4x squared. You have 4x squared times x squared. Now the 4 really, I mean, all I care about is it positive or negative? Because if that lead term is a positive x to the 4th, you get this. If it's negative, you get that. So now any 4th power polynomial is going to look something like this, right? End behavior. You sure we got no questions on the end behavior thing? What was that? Was that a call? A gnaw. Okay, I gotcha. Thought it was like a crow. Okay, so this thing's going to go. Now, if you think about it, it's kind of interesting. It doesn't be very steep, the actual graph. So there's my end behavior. So I can put my end behavior in first if I want. What's she saying?
I don't know. Well, the first place are actually
It's going to bounce off. It's going to come up and pass through the y-intercept. Come over here, bounce off here, and then go off to infinity. There's my graph. Not the prettiest drawing, but yes.
So what makes there, how would you find where it comes off of the intercept or the y-intercept on the right side? How do you determine how tall that little loop will be?
Oh, this hump?
Yeah.
Right now, we're just not going to be concerned with it. There's a technique that you'll learn about in calculus called optimization, where basically you can figure out where this hump is basically has a zero tangent line, and then calculate what x value does that hump occur at, and then plug that into the function. It's one of the more common techniques that you learn about. But for now, we'll just say, the hump could have occurred over here, maybe. So we're not going to be like too worried about it. That's a great question. Thanks for asking.
How do you determine what the graph looks like?
So that was just everything we just talked about. So like, you mean like once you have all the points on there?
Yeah. Because I got all the points on there, but then I decided that it was going to go like that. And
Wait, so
it was not right.
so you
I
can.
have negative half, 0, 16 is the y-intercept, and 4, 0. But like, how do you know it does the wavy thing?
So let's look at a wrong one and figure out how do we know it's not correct. So like, did you have it coming from down here?
Yeah.
Okay, so say you graphed it like this. We know that can't be correct because the end behavior. I know it'd be on the right, whereas this graph that I just drew, there's another mistake here too. What's wrong with this 0 that I drew? Yeah, it's not bouncing there. So now suppose you went like this. Suppose you had the bouncing correct. Well, say you tried to make it come from this side. Bounce. Why is that one wrong? It's missing the y-intercept that we know about, and it has the wrong end behavior. So this last step the last step of actually getting the curve to conform to all the conditions that you just outlined is probably the most challenging part of it. Because the rest you can just do systematically, right? Like you can just go step by step and go y-intercept, plug in 0. X-intercept, what makes that 0? What makes that 0? End behavior, just look at the exponents and, the last step is the tricky, but it's also the interesting part, I think. Anyway, does that make sense? How you can kind of rule out certain shapes? There's no formula, for example, for how to conform the graph to the points. Let's do another example, and we'll take some time to work on our own. Let's look at 12. I'll say 11 is very similar to number 9. By the way, someone pointed out another interesting thing about this graph last class, which was that they said something like, it's always positive, or to be more precise, it's never negative because it's a squared number times a squared number, right? When you square something, it can never be negative. So we know that no matter what you ever plug in for x, stop crinkling.
Right.
So no matter what you plug in for x, it's going to be that thing squared, which is guaranteed to be not negative, times another not negative. So now you can see that in the graph. The whole graph is above the x-axis. We're touching this. Okay, one more example. Okay. We're in number 12. Y equals x times x minus 1 times x plus 2. Okie dokie.
So we know that it's 0, 0, that's the x-intercept. The 1. There's the x.
Very good. So that's one of the first things that might pop out to us is that if I set x to be 0, I'd have 0 times negative 1 times 4, right? So 0, 0 must be an x-intercept. This term would generate what x-intercept? Positive 1. And this term would generate an x-intercept of negative 2. Very good. And I may make myself a note that, by the way, what's the exponent on him? 1, which is odd. So we're going to pass through at 0, we're going to pass through at 1, but at negative 2, we are going to have a bounce. Bouncing. We already got the y-intercept. Let's get the end behavior. All right, so let's see. If we were to expand this whole thing out, what do we get?
X to the 6.
Very good. Excellent. We have x to the 6th plus a whole bunch of other stuff. Is everyone okay with that? Make sense? Okay. And then what kind of end behavior does x to the 6th have? The inside can be all wacky and wonky, but no matter what, it's going to have to do that. Right? Okay, so now this one, we can't say that it's always positive this time because you don't have like a square times a square. You have this term could be negative, this term could be negative, this term can't be negative, but you know, for example, if x is 0.5, you have positive times a negative. Anyway, and by the way, that's one of the ways you can kind of figure out the graph is by just quickly thinking about a couple of numbers like I just said, 0.5. Plug in 0.5. I don't care about the size of the number. I just care as a positive or negative. So 0.5 would give me positive times negative times positive, which is negative. So I can know, for example, that between 0 and 1, the y values are negative. Did that line of reasoning make sense? Okay. So anyway, you got to fit that shape onto this graph with a bounce. So let's start from the left. There's my end behavior. Let's bounce off. Maybe take a break. Okay. This is seriously this idea. You go like, okay, am I still okay? Yes, end behavior is correct. The bounce is correct. Okay, now I got to pass through this point, right? And then I got to, let's see, I got to pass through the 1, right? And then I got to extend out to infinity to satisfy the end behavior. So that's what my graph looks like. And the only improvement I could make, I wanted to be fancy. Again, this is not. Don't worry, I'm not going to like mark you wrong if you don't put this on there, but I just think it's interesting. Yeah, it's at that 1, it's actually a cubic behavior. And so it would actually look kind of like that. I know it's very minor, but I just think it's worth mentioning. It's kind of interesting how the function like remembers where its zeros came from. This 0 was generated by this cubic term, and that's exactly what that cubic term, or that's the kind of behavior you'd see at the 0 in that cubic term. So I don't know. No questions? Feel good? Okay. So why don't you guys try a few? I think that's good for the video. That kind of explains everything I wanted to talk about. Stream over. Thanks for the 100 bits.